and in the other phase the dynamics is not chaotic. Then we actually found out that in the non-chaotic phase, the dynamics of the entire system actually freezes. So the transition actually begins to look like an absorbing phase transition. And then from there, it's a very short bridge to finding out that this transition actually lies in the directed percolation universality class. So that's basically the story. And these are the two papers where these results are presented in all their detail. Okay, so let me get to the meat of the talk. How do we think about classical many-body chaos? So just to make things concrete, let me talk about a model. What we do is not very specific to the model, but just to sort of set the stage. Imagine I have a classical spin system. These are Heisenberg spins. These S's are components of unit vectors. And what I have here is a Hamiltonian, which actually is time periodic. And again, the time periodicity is there for convenience. It's there to sort of get rid of any conservation law that you have, including energy. So because we wanted a system which is devoid of any conservation laws, so that any slowing down that we see in the dynamics, we should be able to attribute it to the constraints and not because of the conservation laws. And the other advantage of a model like this was you could write down the stroboscopic evolution of the spins in terms of simple rotation matrices. Of course, the angles of these rotation matrices change with time, but this just presents a nice computational simplicity. So this is the model, and the way we think about classical many-body chaos is we define a decorrelator, and the decorrelator is nothing but what we do is we start with two initial conditions. They are exactly the same everywhere, except they are different at one particular site, let's say in the middle of the chain. And then we ask that these two copies under this sort of seemingly chaotic dynamics, how do the two copies get decorrelated in space and time? And what you basically see is that there is a ballistic light cone with some spread, with some sort of broadening of this front. That's not going to be rather important. The crucial point is that you see a ballistic light cone spreading of this perturbation. And this is something that in a very different context was thought about all the way back in 1969. More recently, a group of people from ICTS wrote this paper where they showed or characterized this very well in the context of a non-integrable classical spin chain. Okay, so this is the setting. And now, how do we actually think about adding kinetic constraints to this model? So what we do is we say that at the start of every time cycle, the model goes and checks that whether it satisfies, or each spin goes and checks whether it satisfies a particular condition or not. And the constraint condition basically says is a theta function, and it's a theta function of this kind. So it's cos of theta c. Theta c is going to be a parameter in my problem, minus the minimum of all the z components of its neighboring spins. So in words, what it means is that imagine this is a sphere, this is a sector defined by this angle theta c, and what we are saying is that a spin is free to rotate if one or both its neighbors are outside this cone, and this spin is frozen. It cannot rotate if both the spins, both its neighbors, for example, if you think of this being on a 1D chain, then if both its neighbors are inside this cone. And this form of the constraint was inspired by this paper, Fredrickson and Anderson, all the way back in 1984, where they basically proposed this in the context of classical Ising spins as a model for glassy dynamics. So, okay, so this is the model we want to simulate, and once we do the numerical calculations, what we find is that for smallish values of this constraint angle, you have the ballistic light cone just as before, just as you had it in the unconstrained model. But once we increase the theta c beyond some critical value, this light cone gets completely arrested. And what that means is that we really do not have any spreading of the perturbation, and this is what we call the non-chaotic phase. This is what we call the chaotic phase. And it's clear, for example, just between 0.52 of pi and 0.6 of pi, you rather see this very sharp distinction. This sort of tells us that most likely there is a phase transition here. Okay, so how do we understand this, or how do we understand this non-chaotic phase? So what actually happens is, because of the constraints, the front of this decorrelator is not free to propagate in space. So every time it comes to a particular site, it may or may not have to wait for a certain amount of time before it can actually move further right or further left. So if you actually zoom into a particular realization of this decorrelator, what you find is that it's composed of these vertical segments and then and these 45-degree lines. So these vertical segments are basically the times that it's waiting. So from this, you can compute, or you can numerically you can obtain an ensemble of these waiting times. And what we find is that in the chaotic phase, this waiting time distribution actually on a log-log scale, it bends downwards, which means that it's basically decaying faster than a power law. And on the other hand, if I go to the sort of non-chaotic phase, what you see is that it actually has a power law, and this power law exponent is smaller than 2. In fact, at our best estimate for the critical point, we see that this exponent actually hits 2, and that's the point where the mean waiting time diverges. And this is nice because this basically says that if the mean waiting time diverges, then the time taken by the front to move a finite distance also diverges, and that basically means that there is no ballistic right cone. Of course, it doesn't rule out sub-ballistic spreading of the OTOC, but our numerical calculations show that there is no sub-ballistic spreading of the OTOC. So there are only 2 phases in our model where there is ballistic spreading, when there is no ballistic spreading. Now, how can the decorrelator stop spreading? There can be, naively you can think that there are 2 mechanisms. One is there are these, so imagine this is an activity map. So what does this mean? All the red dots here denote spins which are active, which can rotate. And the white regions denote spins which are frozen. So you can say that 2 things can happen. One is that there are rare islands of sort of frozen spins. And what happens is that the OTOC goes here, and then it hits one of these islands and just gets stuck there. So this could be one mechanism. The other mechanism could be that the entire system actually freezes, that all the sites eventually become inactive and the system goes into this absorbing state. Now, since I gave you the summary before, what we find is that this doesn't happen. This is what actually happens. So for example, this is again an actual simulation that for the chaotic phase, the system always has a finite density of active sites. For the frozen or the non-chaotic phase, the activity basically dies down. Okay, so now what we see from these pictures is that these active sites actually form a contiguous cluster which goes all the way down to the set of active sites at the initial time. What is this picture telling you is that you cannot spout an island of active spins if all the spins around are inactive. So from this, basically you sort of there's a hint that this may actually look like directed percolation with an order parameter which is basically the number of active sites as a function of time. Actually, the similarities actually go a lot further. So this is how you typically understand directed percolation. So you have a square lattice or a tilted square lattice. You randomly remove some bonds as you would do in isotropic percolation, but then you say that clusters are only allowed to grow in one direction, and let's call that the time direction. So this is exactly what's happening in our case also. So at some time t, we have a set of spins in a particular configuration. Depending on how the dynamics of the active spins are in that cycle, it might or might not seed stochastically a whole set of active sites at a later time. So if you really think of the active sites and inactive sites as the classification, then it does very much look like directed percolation. And what we then do is we calculate this order parameter, which is the density of active sites. This is sort of the result. For the blue lines are in the chaotic phase, the red lines are in the non-chaotic phase. And what we do is we do dynamical scaling. So we say that at the critical point, scale invariance basically tells me that this should decay as a power law. And away from the critical point, so okay, unlike conventional critical phenomena where you have only a correlation length exponent, here you also have a correlation time exponent, and the correlation length exponent and the correlation time exponent are related to each other by this dynamical exponent. And one can show that if you could really simulate the system up to infinite times, you would have had an order parameter exponent, and which are sort of related to each other by this. But anyway, so we take this data, we try to collapse it on top of each other, we do the finite size scaling at the critical point, and the exponents that we get basically match the known directed percolation exponents to some fourth or fifth decimal place, which tells us that this transition indeed is in the directed percolation universality class. Again, this is back to my summary slide. What I did not show is the whole thing goes exactly in the same way for 2 + 1D. Yeah, and with that, I'll end my talk.
Any questions?
No question. First of all, what is the dynamics? I mean, do you have temperature?
No, we have a driven system. So if I don't do anything, it will heat up to infinite temperatures. So this is the dynamics, right? So if so imagine the constraints are not there, then you have basically some chaotic spin dynamics.
But in the constant model, you do not have this interaction, right? I mean,
generally you don't have this. I agree. Generally you don't have. But here what I'm doing is I'm saying that there is an underlying interaction, and whether the dynamics happens or not is determined by the kinetic constraints. It's not really a part of the Hamiltonian if you want to think about it. Okay, so it's like you apply the rotation if the constraint is satisfied. You don't apply the rotation if the constraint is not satisfied.
And depending on whether you are in the chaotic phase or non-chaotic, is there any sort of effect on the glass-like dynamics? Did you say?
So we computed the 2-point correlator, for example. What we were sort of seeing was that the 2-point correlator saturates to some finite value in the frozen phase, and that's not surprising, right? Because the whole system basically freezes within some cone. So in that sense, although we started looking at the decorrelator, all of this is actually happening at the level of just one copy. So for example, had this been the case, which is why I tried to make a distinction between these two. Had this been the case, you would not have actually seen glassy dynamics, but you would have seen an arrested decorrelator. But it's actually the more sort of boring case that where the entire system actually freezes. But it helps us put it in the directed percolation universality.
Okay, thanks.
Hi, Sthitadhi. So I have a couple of questions actually. So first of all, is there a transition as a function of your angle of constraints?
Yeah, that is the parameter. Yeah.
So is there a sharp transition somewhere?
Yeah, there is a sharp transition. Like it's okay, it's 0.534 something.
Okay, and does it depend on the initial state?
No, it's averaged over all initial states. The result is averaged over because it's a driven Hamiltonian, so I can sort of average. I mean, think of it as an infinite temperature ensemble average.
Right, right. But if you take some of the, for particular initial condition, it can still go by, right?
Go where?
It can have a path, right? Is it
not really? So
no?
That's what I was trying to show here. That for example, these are this is a single realization.
Right.
So you see that in the frozen phase, it really does become completely inactive.
So it happens for all initial conditions.
All initial conditions that we checked, and when you average, the activity does go to 0. So,
okay.
I mean, this is the average activity, and you can see that it's rapidly going to 0.
Okay.
When the cone is at the threshold of
okay, that is a very good question.
It's a little bit like it's not in your last
picture
there.
We don't know. So okay, so what we could do was we took these decorrelators and we computed the butterfly. Okay, we call this the butterfly velocity and the exponent with which it broadens. The exponent did remain very close to 2 all the way up to the point where we could, or half rather, all the way up to where we could, satisfactorily fit the data.
Right.
But the velocity did go down. But we didn't have enough results. For example, it's very difficult to fit this data. So we didn't know what to sort of do. So that is one thing that we don't know is to how to characterize the phase transition in terms of the decorrelator. Like,
what is the standard thing in the DP literature for the analog of this?
So in DP, what they do is they look at damage spreading. Okay, but in damage spreading, what they do is they don't look at spatiotemporal correlations. They only look at the density of damage sites, which is what effectively we ended up doing. Like not in terms of damage, but in terms of the activity. And we just looked at the density of active sites, and we did the critical scaling in terms of that.
Right.
So you said that it goes the same way in 2D.
2 plus 1. The exponents change, of course, but yeah.
But so is the non-chaotic regime reduced in parameter space?
Sure. I mean, of course, the phase transition happens at a larger theta c.
Okay.
That's what you expect in 2D anyway, because it has more chance to speed up.
And do we know anything about the quantum versions of these problems?
Well, that's what we are trying to work on, but difficult to do these kinds of things with 20 spins. So that's the problem.
Yeah, I have a question. So you do the Poisson bracket dynamics in between, right? I mean, but let's say if you do a Monte Carlo dynamics, like so where you can in principle go out, right? Because I mean, with some probability you can flip. So will you still get this arrested state?
So there is a paper by Johannes Nolle Roderick who tried doing this for Ising spins with this Glauber type dynamics, and they do see a similar transition. So we didn't do this, but they did this. So they had Ising spins, and the difference in the initial condition was they took some Ising, like classical Ising state, and then they flipped one spin in the middle, and then they were asking, and then they did Glauber dynamics, or they basically did not exactly Glauber dynamics, but they did a version of a cellular automaton. It's called the Kaufman cellular automaton. In some limit, it does become the Glauber dynamics, and there they saw very similar.
So your case, completely random initial configuration, you get this one, meaning infinite temperature type configuration.
Yes. Now, whether there are some measure zero initial conditions which don't show this.
I mean, if you start with all active sites, maybe it will move.
No. So actually, if this is something. So okay, that's a good point. So here we actually started with all active sites. So we wanted to make sure that the initial condition is. So here we did start with states which are random, except all spins were outside the cone. So you see that the activity does start. Okay, this is already the first time step, but at the 0th time step, the activity is indeed 1. So we did start with a state. This is actually just to be careful about the initial condition not creating blockades. So for these plots, I mean, of course, if I sum over all initial conditions, these plots look quantitatively different, but the exponents don't change. But we did actually start with all active spins.
Same question as Arnav. So if you're near the critical point, do you see large sort of sample to sample fluctuations, like, or is it you don't see any
sample to sample fluctuations?
Like sometimes it's percolates, sometimes it doesn't percolate. I mean, if you're close to.
Yes, right. I mean, that always happens, right? Because it, like, if I'm slightly to the slightly on the frozen side, it might, or let's say I'm slightly on the chaotic side. For a particular system size, I might see, but who knows that if I actually simulate it for larger, somehow there will be some small activity pattern which will.
So it's same as in.
Same as any critical phenomenon, because all of this is numerical, so the same issues as.
If no more questions are there, let's thank the speaker.